Hey everyone, this is going to be our final video on chapter 8. So again, worth celebrating. Good job if you made it here and you've been keeping up. If you haven't, well, it's never too late. This section called 3D Composite Figures is not actually part of the textbook. However, as opposed to going into chapter 9, our Northern department thought it was a good idea to talk about 3D composite figures because let's be honest, up until now when we dealt with composite figures, it was always in 2D. Just to refresh your memory, if I gave you a shape like this, what kinds of regular shapes do you see? You might say, hey, I see a large rectangle, I see a smaller rectangle, and then I see a triangle on top, right? And that's all good and all, but you have to be able to use that same kind of thinking and sort of dismantling process with 3D figures. Why? Well, what kind of world do we live in? 3D. We are not like 2D flat beings, right? We're not like pieces of paper walking around. That would be weird. So what I mean by that, here's an example. Like, summer's approaching, spring is here. So let's pretend with the social distancing stuff all lifted, you go outside, go to your local Baskin Robbins or some kind of ice cream store, and you get yourself an ice cream cone, right? And then you think, oh man, I've been doing so much math. Everything I look at is math. Like for example, this ice cream cone with this huge scoop on top is essentially a cone and half of a sphere, right? Like if this was a perfect sphere and I decided to cut that in half, that's basically what it is, right? And so if I ask you something like, Dairy Queen, famous for their chocolate dipped ice cream soft serves, they want to do a promotional where they take this entire thing and coat it with chocolate. That's right. Even the handle, and all your hands are going to get messed up and messy when you buy it. The entire thing is going to be coated with chocolate. How much by volume chocolate do I need to cover the entire surface? And you'd be surprised what the kinds of calculations that I'm going to say, I guess food industries and companies, we actually try to do to save as much money as possible. Because let's be honest, if you save 1 cent per cone, how many cones do you think those huge conglomerate companies are going to sell in one summer? 1,000? 100,000? 1,000,000? 5 million? I don't know. But let's pretend 0.01 cent is what they save per cone. Multiply that by 1 million cones sold over the summer, which is actually a really small number. Do the math. It automatically becomes 1, 2, 3, 3, 3. 1 cent per cone becomes $100,000. Oh, sorry, $10,000 saved, right? And that's a small number compared to North America, all of North America, South America, wherever that you sell ice cream cones. So 1 cent is a huge deal, okay? So let's talk. When I give you a shape, your first goal is to be able to break it up into, I guess, easier or normal 3D shapes, and then figure out, let's say for something like surface area, what is the actual surface? In this particular diagram, the surface would be, and this is where your knowledge of formulas come from, the surface of the entire ice cream cone is the surface area of the cone ice cream. Wow, the surface area of the ice cream cone is the lateral surface of a cone, not the base portion. I don't want that. Plus half of surface of sphere. So again, if you've looked at the past chapter just by memorizing formulas, you're going to be screwed because there is no formula for a cone, like an ice cream cone. If you recall, the lateral surface of a regular cone is pi rs. And then the half of a sphere would be 4 over 3 pi r cubed. Okay? Just to jog your memory, where does a pi rs come from? Remember, the surface area of a regular cone was pi rs plus pi r squared. This part was for the circular base, and this part was for the lateral. I only want the lateral. I do not want the circular base. So yeah, it's important. At this time, if you want to pause the video and actually print out or somehow get in front of you the worksheet that I posted on our Google Classroom, because this is not exactly part of our textbook, I am going to ask you or run through questions together from our sheet. Okay, we're going to do example 1 and example 3 together. I'd like you to try all the examples and practice questions that we don't do on your own. And that's going to be your week assignment. Starting next week, you will see, I can believe that we're going to start up with our culminatings. Okay, so we're approaching the end of the year. So congratulations and keep working hard until the very end. Clearing the screen in 3, 2, 1. All right. I have with me, I want you to find so example 1 of our sheet. What is the surface area and volume of the composite figure? And the composite figure that I posed is basically sort of like a shape of a house. There is a cube followed by a pyramid right on top. Okay, so I'm going to try to draw that just to make sure that we're on the same page. Please bear with me. This is supposed to be a cube. Now you'll see me make little marks so that you're not completely confused. Oops. And then there is a pyramid. That's supposed to be a perfect pyramid. Sorry about that. Okay, here we go. Being a cube, the height, the width, the length, they are all 10 centimeters, right? And the slant of our pyramid, so the slant of our pyramid is going to be 12 centimeters. Okay, step 1. Let's break down the different shapes that we see. Number 1, we see a cube. Good. Number 2, we see a pyramid. Okay. Yeah. And just in case I get certain things wrong, no, I should remember the formula. I should be able to remember. All right. Here we go. Surface area. I'm going to start by highlighting the surfaces I'm going to deal with. For the cube, the surface area would be a square surface here, a square surface here, a surface on the side, and a surface on the back side of this picture that we don't see. Do I have to look at the surface of the bottom? Well, seeing as how this is not exactly a house, I'm going to say yes. All right. But if this was in the context of, let's say I'm building a house and I need to paint the house, we're not going to paint the bottom of the house because that's where the soil is, right? But in this particular case, it's just a shape. It's like a, like a wooden block and placed with a wooden pyramid on top of it. I'm going to pretend the base is also part of the surface, right? That's for my cube. So let's write this down. Number 1, for my cube, the surface area of the faces is length times width, 10 times 10. And how many do I have? The sides are 1, 2, 3, 4. This is going to be 400 centimeters squared. the surface area of the floor, which we can't really see right now, but it is sort of there, it's going to be, again, 10 times 10, which is 100 centimeters squared. The surface area of the cube portion is 500 centimeters squared, 400 and 100. And please note, I am not adding the surface area on top of the cube because, again, it's not a surface. It's not exposed. Okay? That's why I'm not adding that extra portion. Let's move on to the pyramid. I'm going to do that in, let's do blue. The pyramid has a surface here. That's one triangle. It has another surface here. And of course, being four-sided, it has two other triangles that we do not see. Well, what is the area of a triangle? Okay, it's, well, base times height divided by 2. Well, this triangle right here, what is the base? That's a 10. But what is the height? Ooh, think about it. Going once, going twice. You can't calculate directly. If you said it was 12, you are unfortunately incorrect. I'm going to take this bent over, slanted triangle, and I'm going to stand it up on its feet. The base of this triangle is 10, and according to this image, the side length is 12. What I want is the height. Can you guess how we get there? 3, 2, 1. Hope you got it. We pretend this is a right angle triangle with the base being half of 10 so that we can use Pythagorean theorem. So 12 squared being the hypotenuse is 5 squared plus h squared. 144 is equal to 25 plus h squared. That means 119 is going to be h squared, and I cannot do that in my head. Height is going to be approximately 10.9. Now we can do the area of my triangle. Base, a half times base times my height, because my height is 10.9. That is going to be equal to 54.5 centimeters squared. How many triangles do I have? 4. Area of the total, the surface area of the total pyramid would be 54.5 times 4, which is 218 centimeters squared. It's a bit long-winded, but this is what it takes to calculate surface area. So the total surface area would be 500 for the cube portion, 218 for the pyramid portion, 718 centimeters squared. All right. The volume is a little easier, so I am going to try to squeeze that here. The volume of a cube, because I'm talking about the inside of the shape, in other words, how much space is actually covered. I don't care whether the surface is exposed or not. I'm talking about the filling. So I don't have to worry about cutting anything out in this particular case. Cube volume is length times width times height, which is 10 times 10 times 10. In this case, it is going to be 1,000 centimeters cubed. The volume of a pyramid, did I cut any pieces out? I don't think so. This is a regular pyramid, which is a shape that we can shave out or cut out of a rectangular prism, length times width times height. Here's the problem. Do I have the length? Yeah, I do. That's a 10. Do I have the width? Yeah, I do. Do I have the height? of this pyramid? No. Any thoughts? Any thoughts at all? You know what? I'm going to erase this. While you think about it, let me erase this because I realize I might need more space than I thought. Think about it. How might you calculate the actual vertical height of that pyramid, not slanted height? And hint, of course, the slant may come in handy. Another hint, earlier in our chapter, we talked about a question where I asked you to calculate a diagonal height of a 3D structure, or diagonal slant of a, what is it? The space diagonal of a cube. For my pyramid, knowing that this is a 10 and knowing that this is a 12, and I need this height, here's what I'm going to do. Assuming that this is a perfect pyramid, which it is, right, 10 by 10, the location of the height is perfectly in the middle of my square base. That means it should also be perfectly in the middle of my diagonal. So if I find the diagonal length across the base of my pyramid, if I cut it in half, that essentially creates a right angle triangle for me. See if you can think about that one more time, okay? I have with me a pyramid, and the pyramid center is going to create a 90-degree triangle with the hypotenuse of 12, the height of something, and the base of something, right? So using a highlighter with a different, I'm going to pretend, because this is a square, this is going to be a right angle triangle, and I'm going to redraw that out. Do you see it? Let me try to color coordinate it. This green portion right there is right there. Using Pythagorean theorem, my hypotenuse, x squared, is going to be 10 squared plus 10 squared, which is 100 plus 100, that's 200. X is going to be the square root of 200, which is 14.1 approximately. Okay, if this entire diagonal is 14.1, that means the halfway point would be approximately 7.05. All right, that means this height, this base, and that hypotenuse portion is going to be 7.05 centimeters. That's going to be a height that we do not know. And that slant diagonal is going to be 12. So 12 squared is equal to h squared plus 7.05 squared. That means h squared is going to be 94.3 approximately. That means the height is going to be approximately 9.71 or 9.7. So bring that back to our original. The pyramid volume is going to be the length, which is 10, width, which is 10, and height, which is 9.7. 10 times 10 times 9.7. The total volume of the pyramid is 323.3 centimeters cubed. Therefore, total volume of this entire shape is 1,323.3 centimeter cubed. Now I know this can be challenging, and it's meant to be. So if you can't get this on the first try, then don't be discouraged about it. Oh my goodness. The whole point is to be challenged. Because after all, if this was easy, anyone can do it. Anyone would be a famous math. No, that's not what we're trying to get at. We're not trying to test your brilliance to see, oh, you're good at math, you're bad at math. No, this is about becoming better. This is about becoming more a proficient critical thinker. This is about looking outside the box. This is about thinking and trying to problem solve ways that seem impossible, but there is a way if you keep on working at it. Okay, and that's a transferable skill that works everywhere. I'm going to clear the screen again, and we're going to try example 3 from the sheet. All right, clearing in 3, 2, 1. So example 3 of our worksheet says something like this. It says, a silo shown at right is to be built from metal. The top portion is a cylinder of diameter 4 and height 8. The bottom part of the silo is a cone of slant height 3. The silo has a circular opening of radius 60 centimeters at the top. What area of metal is required to build the silo? All right, let me draw this first. And we try to, as opposed to typing everything in, I think it's better that I do it as a 4, 8, 3, and 60 centimeters at the top. So, I shouldn't do that. That's 8 meters. The diameter is 4 meters. Okay, and the slant is 3 meters. And there is a small opening with a, what did it say, radius or diameter? Oh, small, with a radius of 0.6 meters. So it's 60 centimeters. All right, grab your bearings and recognize that this is a cylinder and a cone. It asks to build out of metal, which means if I'm going to build this, am I filling this with metal? No. What they're asking for is a surface area if I have to make this out of metal. If you're not sure what a silo is, you could think of a silo as a large container that is made to store resources, particularly in agriculture like farming. You could fill a silo with wheat or hay or whatever resource you might need to survive the winter, or you might want to stock up before you sell, whatever. Okay, let's talk about this. Game plan. I am going to look at the surface area of a cylinder, right? The side surface area. I also need to consider the top surface of the cylinder, but of course there's a little hole there, so I have to cut that out afterwards. I don't have to worry about the base of the cylinder because it is not a solid piece. Instead, the surface that is supposed to be the base of the cylinder is replaced by the surface of a cone, right? And in terms of the cone, I only need to think about the lateral surface of the cone. I don't have to, again, worry about the base of the cone, the circle portion of the cone, all right? So let's talk about this. In terms of the cylinder, if you recall, the formula for the surface area of a cylinder is 2 times pi r squared, because this is the top bottom portion, right? It's a circle, okay? Plus the side of the circle, side of the cylinder, which is 2 pi r height, right? Think very carefully now. Which part of this formula do we need, and which part of this formula do we not need because of the context of this question? I hope you said, I need one circle, one of the circle, not 2, and I need the side portion. Okay. Next, what part of the cone do I need? For the surface area of the cone, we have pi rs, which is the lateral surface, and pi r squared, which is the circle portion. In this context, we don't need the circle portion because that is covered. So for this question, we are adding pi r squared of the cylinder, 2 pi r height of the cylinder, and pi rs of the cone separately, all right? So in your head, maybe you wanna put a little division there so that you know which numbers to use. Surface area, specifically for the cylinder. The cylinder has a radius of 2 meters because, you know, the radius of the cylinder, the diameter is 4, so the radius must be a 2. Plus 2 pi r, and the cylinder has a height of 8. So that would be 4 times pi plus 2 times 113.097 meters squared. I'm going to round it to 113.1 meters squared. I forgot one piece. I have to cut out a little hole because a silo isn't supposed to be completely sealed. I need a place where I can store stuff. I need to throw stuff inside, right? Sort of like a pit, and there's my entrance. So what is the surface area of the hole? Well, that's just the area, just basically the area of the hole, right? It's not a surface, just it's pi r squared. Pi, the radius is 0.6 squared. So that gives us 1.13097, which I'm going to round to approximately 1.1. All right, so bringing it back, the total surface area that I am interested in is 113.1 minus 1.1. It's going to be about 112 centimeters for the cylinder portion. Now let's work with the cone. The cone is pi. The radius of the cone is still the same as the cylinder. That's a 2. The slant is given to us, thank goodness. Otherwise, we would have had to calculate it. So that would be 6 times pi, which is approximately 18.84955, which I'm going to round to about 18.8 meters squared, right? So the surface area of the cone portion is going to be 18.8 meters squared. So that means the total surface area is 112 plus 18.8. It gives us approximately 130.8 meters squared. And as the question says, of metal is needed to build this. Okay, that's part A. How do you feel? You might want to pause the video and try it again. If it costs $12.50 per meters to cover with anti-rust, that makes sense. If you didn't know, if this silo is buried underground, which I believe it is because the base is a cone, I don't think that you'll be driving along the landscape and then all of a sudden see a silo standing on it on a tip, right? That would defy gravity, I think. Anyways, if I had to coat the entire thing with anti-rust material, because the soil is damp usually, and there's rain and blah, 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 and if there's rust, it spoils all the food, how much would it cost? Well, the total surface area is 130.8. So I have 130.8 meters squared, and that's multiplied by 1250 per 1 meter squared. Why did I multiply it in this way? Because by unit conversion, if I want to get rid of the meters and I want to change it to dollars, meters need to be on the top numerator and the denominator so that they will sort of divide each other out, leaving us with just the dollar sign on top. 130.8 times 1250 is going to be $1,635 just to code, just to buy the material for this. You see how this can be applicable to a little bit of easy business 101, right? Cost versus, I guess, profit. We'll see. The other questions, sort of example 2 of the sheet, as well as the practice questions that I provide for you, they are all sort of mixes of this where you see multiple formulas coming together to make sense of a story or some kind of scenario. Please try your best. This is basically, in my opinion, the upper echelon of trying to critically think. Again, for those of you who have been memorizing formulas until now, you're going to really, really have to think harder about this. It's not as simple as just copying a formula down. Do your very best and ask any questions through email or through posts, and I will try to help you as best I can. Best of luck.